right, welcome to the COPRI Coastal Engineering Sciences Committee Technical Lunch and Learn. This is the fifth in a series of technical webinars organized by the COPRI Coastal Engineering Sciences Committee. For those of you that haven't attended any of them previously, we plan to host a technical webinar every few months on varying topics that are relevant to people with an interest in the coast, whether they be engineers, scientists, planners, officials, or just coastal residents. Some of you are likely familiar with COPRI, and some of you may not be. COPRI is the Coasts, Oceans, Ports, and Rivers Institute of the American Society of Civil Engineers, or ASCE. Within COPRI, there are many ways for interested practitioners to get involved through local chapters, technical committees, and also student chapters. The Coastal Engineering Sciences Committee is one of several technical committees within COPRI, and one of our core initiatives is outreach. Our group developed this technical lunch and learn series to provide a way for the coastal community to engage with each other and learn about recent large and impactful projects and also interesting research. We open this up on a national platform and hope that it fosters discussion and idea sharing during these days when conferences and workshops are still somewhat limited, maybe not as limited as they were this time last year, but still somewhat limited. And today we have over 130 registrations from over 10 countries. No pressure, Bill, but a pretty diverse audience. While we call this a lunch and learn, we realize that there are attendees from all over, so it may be a breakfast and learn for some or something else for others, but no matter what time it is, we're glad you're here. On to today's presentation. I'd like to introduce Dr. Bill Daly. Dr. Daly is a professor of civil and coastal engineering within the Taylor Engineering Research Institute at the University of North Florida. Prior to his time at UNF, Dr. Daly has also served as faculty at Florida Tech, otherwise known as the Florida Institute of Technology, back when Dr. Daly was there. And before that, or after that, he started his own R&D and consulting company, SURFBREAK Engineering Sciences, which remains active to this day. Dr. Daly earned a bachelor's degree in civil engineering and a master's degree in coastal engineering from the University of Delaware, and his Ph.D. from the University of Florida. Go Gators. Dr. Daly's education, research, consulting experience, and publication record encompasses fundamental theory, numerical modeling, physical modeling, as well as laboratory and field data collection and analyses. Today, Dr. Daly will speak about SURFBREAK analysis and engineering. We plan for Dr. Daly to speak for about 35 to 40 minutes, which will leave plenty of time for questions and discussion following the talk. Please type in your questions during the presentation, or after the presentation, you can raise your hand, and we could also unmute you to allow your question and have an interaction with the response. But we won't be stopping the presentation for questions midstream. We'll save those all for the end. And Dr. Daly has mentioned he's going to go through his slideshow, and then he has several videos to show at the end of the slideshow that illustrate some of the points made during the presentation. With that, take it away, Bill.
Okay, welcome everybody, and thanks so much for attending. I'm going to stroll down a lot of memory lane here, so bear with me. Let me get there. Let's see. For some reason, there we go. Okay. So this is an outline of my presentation, and I won't read it all to you, but I'm going to start out mostly with kind of the science, or what you might call science, behind SURFBREAK analysis, and then go into several of the options we might consider as engineers to improve SURFBREAK. And I hope I'll be going pretty quickly, so if you miss something, just let me know when we get to the end, and I'll go back to that slide. But anyway, with that, so who cares about SURFBREAK? In our profession, most of the beach concerns are with nourishment and erosion and those sorts of things. But back when I started at the Florida Institute of Technology back in 1987, shortly thereafter, Steve Hughes from the Coastal Engineering Research Center, which had become Coastal and Hydraulics Laboratory in Vicksburg, called me and said, Bill, you're a surfer, aren't you? And I said, yes. And he said, well, how would you like to come to Huntington Beach and speak to a group of 200 angry surfers about this project that's planned? And I said, oh boy, what fun. Yeah, let's do it. So the Signal Landmark Company wanted to, in exchange for donating a large section of oil polluted wetlands to the state, they would give this, donate this land if they would allow the company to cut an inlet through a state park beach, put in 2 very long jetties and a 3,000-foot offshore breakwater. And the local surfers were justifiably concerned. This was one of their favorite surf spots. So they had a public meeting. I had visited Vicksburg, and they had actually had a physical model of the project. So I wasn't tasked with giving one opinion or another, which was nice. And I told them the bad news that the breakwater was going to take away 3,000 feet of surfable break, but that the jetties might actually enhance the break during times when the waves were coming at sharp angles. So anyway, people do care about surfing, and so the idea of SURFBREAK, this whole project got me thinking, well, what makes a wave surfable, and how can you put a number on whether a certain spot is surfable in case you have to do mitigation or something. So I went back through the literature, and one of the first people to investigate it was James Chemo Walker, who did his Ph.D. dissertation, University of Hawaii, and he defined essentially what makes a wave surfable, and that is that the maximum attainable board speed that the surfer can obtain has to be greater than the peel rate, the rate at which the peel point is moving along the wave. Otherwise, the wave closes out, and of course, sometimes with catastrophic results. So a few definitions here. This vector might represent the actual direction and speed of the surfer. And these are the non-breaking part of the waves. These are the breaking part of the waves. And so the surfer is trying to maintain him or herself along the path of the break point. And so you define that path with this unit vector script L, and that path makes an angle to the wave crest called alpha sub b. The wave celerity is important, as we'll see. So that's C sub b. And then finally, the effective, what I call the effective board speed of the surfer, is just this vector dotted onto the direction of the path of the breakpoint. And finally, the peel rate, then the speed at which the breakpoint moves along the wave crest, is simply given by the celerity of the wave divided by the sine of the peel angle. So with those basic definitions, it really comes back to, okay, can the maximum sustainable board speed of the surfer be greater than the peel rate of the wave? And if that's the case, then you have a surfable wave. If it's not the case, then the wave closes out, and that's the end of the ride. So a long time ago, we started trying to get an idea of what was the maximum speed of surfers. So we actually just rented VHS videotapes of surfers. You used to get at Blockbuster, and essentially, since the frames are exposed at 30 hertz in old VHS, you would look for a line or a piece of aeration, in this case, in the water, and then click through how many frames it took for the surfer to go past the wave, and had to estimate by eye what length of the board was and how tall the wave was. But we ended up with this collection of data, and we noted the breaker type, but breaker height, this is the distance that was traveled as the board passed over that line of demarcation or whatever, and the number of frames, and finally the computed board speed here in meters per second. If you plot that board speed, sustained board speed versus breaking wave height. Oh, and by the way, the frame or the clips that we picked out of the video, the surfer is just screaming along the face of the wave and doesn't have time to do any acrobatics or anything. So that's why we call it a maximum sustainable board speed. So if the peel rate is less than that, often the surfer actually has to cut back to keep within the peel point. But anyway, if we plot this data to a best fit power law, it comes out with an exponent of 0.488. So the light bulb or the bell started ringing, and that tells you that the board speed seems to be governed by Froude scaling, and so we force this parameter to 0.5, and here's the curve. And then these are data points from Kimo Walker's work, where he was actually triangulating on surfers in Hawaii, and even noted many of the surfers were not screaming along the face of the wave. They were doing cutbacks and things like that. So you would expect these data points to fall below this curve. And here are just a few that fall above the curve. So we were pretty surprised, but pretty pleased with that. So we did have a handle on maximum sustainable board speed as a very simple function of breaking wave height. So moving into the probabilistic modeling and how do you put a number on surfability. So we I'm going to walk through this pretty quickly, but we're going to start with a Rayleigh distribution for wave height out in deep water, and that's usually a pretty good assumption. And then just a progression of transformation of random variables. We're going to go from deep water wave height to the wave height at incipient breaking, and then using the results we just saw, we'll get the maximum sustainable board speed. And then this is where we really had to punt. We really didn't have any data on the sign of the peel angle. So I just picked the beta distribution because it seemed pretty flexible, and you'll see some plots of that in a minute. So we go from the PDF of the sign of the peel angle to the peel rate. And of course, when the wave closes out, the peel rate's actually infinity, and you don't want a singularity like that in the middle of your probability density function. So we then have to change the random variable to 1 over the peel rate. And then finally, we're going to assume that the maximum sustainable board rate and the peel rate are independent random variables, and just multiply the two probability density functions together to get a surface of surfability. So most of us are familiar with the Rayleigh distribution. And I just want to make note that H sub RMSO is the RMS value out in deep water. And once again, this is our sequence of the transformation of random variables. So our board speed, from maximum sustainable board speed, from that little bit of video work we did, ended up with a very simple expression if you knew the breaker height. But predicting the breaker height can get really complicated, but it's generally a function of the deep water height, the wave period, and the local bottom slope. The other big caveats were, shoaling waves are highly nonlinear, and using linear wave theory just wasn't going to cut it. So we adopted the results of canoidal theory posed by Schuto all the way back in 1974. And then finally, we need a function that relates wave steepness and bottom slope to the incipient breaker condition. And we just adopted Weigel from 1972. So here's the offshore distribution of the wave height. And then as the waves shoal towards the break point, of course, the waves get bigger. And this is a case of, this is an example for a 1/50 slope. And lambda is our relative wave steepness, HRMSO over L naught. And we see that high steepness waves don't shoal as far as low steepness waves. And I've noted the cutoff for the highest waves, because we know surfers, of course, don't surf every wave, and they surf usually only the largest ones coming in. We're not sure what that number is, but we just took a guess at 1/10. So here's the beta distribution. It's basically, the shape is governed by these two parameters, R and T. I'll show you some plots here in a second. And if you have data on the sign of the wave angle, you can, by method of moments, you can compute what R and T are if you have the average wave peel angle and the variance in that. So once again, we'll be transforming the random variables this way. And I note that if you have a range of kappa, which is wave height to water depth at breaking, this is the range in Weigel's formula, that you get a range in the critical peel angle. So if the height to depth ratio, it's incipient breaking, is 0.8, you need a wave angle of about 50 degrees or greater to have a successful ride. And so same thing for, this is the other limit on Weigel's formula. And for that, you just need a peel angle of 33 degrees or greater. So this is what the beta distribution looks like. And this curve here would be closeouts, waves that are pretty much just closing out. You need to have waves with peel angles that are outside to the right in this case, or to the left in this case, of these dashed lines. So if we have a lot of rights, we can make that happen with our beta distribution with a T of 6 and an R of 4. we notice that the T controls the spreading of the distribution, and R controls whether you're going to have right-handed rides, meaning from the surfer's perspective, they're surfing off to their right, and likewise off to their left. And this just shows what happens when you change T. You can push, you'll end up with more waves in the surfable range than in the previous slide. So it has a lot of flexibility, and we hope to get data that will help guide what parameters need to be, how they need to be set. So we finally multiply we render the board speed dimensionless by taking the square root of HRMSO and the peel rate, and then we make this one last transformation random variable. And for closeouts, that bell-shaped curve where the waves are coming directly on shore, or most of them are, we get big zone of closeouts, and we get a zone over here of right peeling waves and a zone over here of left peeling waves. But if the surfers are only surfing H1/10, that really cuts out a lot of the rides that you could get if you were surfing every wave that came in. And this just shows if you decrease the wave steepness, it stretches the probability density function and narrows it slightly. So, and you do end up with a little bit more surfable waves. And this is the case for rights and lefts that was in the earlier slide. And if you integrate from the highest 1/10 waves that are surfable, you get very small numbers, almost depressing. But anyway, that's what it is. So at the moment, let's pause. If you wanted to characterize the long-term surfability of a particular site, then you would want to have a good idea of the climate of HRMSO and T, this little T, which is a function of wave period. So, so if you wanted to do long-term surfability, then you'd be transforming these random variables as well. The surfer's paradox, that I call it, is that on a sandy beach with smooth bathymetry, if we're getting really nice big long period swell coming in here to Jack's Beach, like from a hurricane going up the middle of the Atlantic, just due to refraction, those nice long period swells tend to close out. So just when things are getting good, the rides get short and dangerous. So since we really can't control the height of the incoming wave, the only recourse we really have, or think we have, is to change alter the bathymetry locally to change the peel angle and push it more into the surfable range. And so this is where we get into the engineering aspects, and this was the idea behind the artificial surfing reef. So I'll be showing this animation hopefully at the end of the talk, but basically this was a feasibility study for a artificial submerged surfing reef done for Brevard County, Florida. And what you sort of see just in this still frame is that the wave is going to peel along the structure here and along the structure there, and at least two people will get really good rides at a time. And the animations that I'm going to show you are all done with Cool Wave, which has been around since 2002. And it's a really good model for this type of work. It is a Boost and S-based model, so you do get a lot of the good nonlinearity in the waves that we're looking for. You can sort of see that here in this transect of what the waves look like. The problem with surfing reefs are that they're very expensive. And I refer you to this very nice article by Tom Shand that appeared in Shore and Beach a few years back. But he, at the time, listed all the artificial surfing reefs in the world, and their price tag was between 1.2 and 3.6 million dollars. That's a lot of money to spend for maybe 3 or 4 people fighting over those 2 breaks. Of course, if we were to try and build one of these here in Jacksonville, where we have sometimes 6-foot tide ranges during king tides, trying to establish the correct or the best elevation of the top of the structure is going to be really hard. You're only probably going to be able either to surf low tide or surf high tide. It's very sensitive to wave direction. As I mentioned, there are only 2 takeoff locations. If they're made of hard material, even sand-filled containers are pretty hard to, they hurt a lot to fall on. The other issue is if you've got 2-foot waves coming in, this expensive surfing reef is not going to make that sow's or silk purse out of a sow's ear. So anyway, that moves us into a second engineering solution, maybe for improving surfability. And it was inspired by an analysis that we did of First Peak at Sebastian Inlet, Florida. So Sebastian Inlet is just below Cape Canaveral, and it's right at the boundary between Brevard and Indian River counties. And they were getting ready to rehabilitate this crib structure, and the local surfers were justifiably concerned that it was going to affect a world-renowned break called First Peak. This is where Kelly Slater, the multiple world champion in surfing, learned how to surf. And people, all the local surfers, knew that even if it was flat somewhere else, everywhere else along the coast on a particular day, you can almost always find something surfable there at First Peak. And in fact, when the waves were big enough and coming out of the right direction, you would get First Peak, a second peak, and even a third peak. Everyone kind of knew this had something to do with reflection off the jetty, but nobody really had a full explanation as to why this break occurred. And so we tried lifting a high-8 video camera over First Peak using a helium balloon. And that was kind of problematic because the winds were usually onshore. So we had to deploy it from the top of a boat at anchor. It was not easy to move around and position ourselves. But this picture does show this was a summer day. It was flat everywhere else. And here are about 6 surfers in the water surfing at First Peak. So we punted and actually built an undistorted fruit model, 1:35 scale, in the side yard of my good friend Dan Oshesky's house. And so I've flipped it here. So we're looking onshore now, but and this picture was taken at night because that was the best. We had to use artificial lighting to actually light up the waves. But if you follow this, this is the incident wave coming off the the wave generator, which was just a very simple flap generator. It's colliding with the representation of the crib structure of the North Jetty and makes a small reflected wave that is trapped to the shoreline by refraction. And this is the key to making first peak. If this structure is more shore parallel, then you send the energy of the reflected wave is sent out to sea and not trapped to the shoreline. So it's this trapped refracting reflected wave that makes first peak. And I'll show you a hopefully show you an animation here that was again done with Cool Wave of just that situation at the end of the presentation. So another issue that often comes up with surfers and the things that coastal engineers try to do with beaches is beach nourishment. And so the Philadelphia District of the Army Corps of Engineers had put in a beach nourishment project in Surf City at Long Beach Island, New Jersey. And the surfers were quite upset for two reasons. One, they buried a groin field that stimulated a lot of surf break. But even more importantly, the big lump of sand put out here with using our conventional, pump it up on the beach and move it around with bulldozers approach created a lot of wave reflection that disturbs the surf break. Any of the surfers on call, I'm sure, have been in conditions like this where the wave peaks up and you start paddling real hard for it, and then it just dies. And what just happened was a reflected wave passed through the incident wave and tricked you into thinking you were going to get a ride. So anyway, I'll show an animation of this at the end. But the big point is right after nourishment, we go from having a wide surf zone with 3 waves in it to a narrow surf zone with only 1 to 2 waves in it. And it took almost 2 years for the profile to equilibrate and for the surfing conditions to return to something more normal. So what I would like to propose is to use some of the nourishment material to build what I call just surfing shoals, excuse me. The idea would be, okay, you might widen the beach enough for everyone to get their towels on it, but finish the project off with these dollops of sand in the surf zone, which could very easily be placed by rainbowing the material. And then, of course, these will only be ephemeral. They'll smooth out depending on their size. But at least the engineer will be a hero to the surfers for a little while rather than a villain. And again, we've done some work with Cool Wave to see if we can replicate that, and I'll get to that. I'd also like to point out this is Mayport Naval Base, which is right here in Jacksonville. This is the entrance to the St. Johns River right here. And they had just done a bypassing project where they pumped sand from the north side to the south side. And there apparently was no stipulation as to how this material was supposed to be shaped. So the dredging contractor just left the pipe there and just let it rip and built this really large salient here. And word has it that the point break that they got here lasted about 2 years, and the surfers loved it. Of course, they also risked getting shot at because this is federal military property, so you had to take your chances. So what's next? Well, lots of people are starting to instrument surfboards for a variety of reasons, but here's one particular case where they instrumented the skeg of the surfboard and were able to collect data on the speed of the board. So there's a way to get directly at maximum sustainable board speed, maybe. They're also instrumenting surfboards more to monitor the shape of, or the flexing of the board and the performance of the boards. But that's one idea. And the one I'm really excited about and hoping to get in here during my sabbatical next year is drones. We just recently, I'll show you a video clip, but having a drone hovering over a bunch of surfers makes it very easy to measure the peel angle, the speed of the waves as they break, the peel rate, the board speed, and we can also get a head count as to how many people are getting rides and how long the rides are, all kinds, it's a wealth of information. The only thing we haven't quite figured out with the overhead video is we can't get wave height of each particular wave. So we might have to resort to having a second camera on the beach looking offshore. And so this is what the drone video will look like. Chris, how am I doing on time?
You're doing fine. I know you're about ready to go to your videos. You mentioned
Yep.
those were
Okay, great.
You're good.
So with that, the epilogue on the Bolsa Chica development project, just in case you were wondering, Surfrider Foundation was successful in halting the project in 1989, and the state began buying this heavily polluted region here in 1993 and created the Bolsa Chica Ecological Reserve. And you can look up on their website. It's really a marvelous place now. And they finally decided that in order to improve the water quality, they really did need an inlet here. But as you'll see, or as you can see, it's a very small inlet with very short jetties. They actually have trouble keeping this open, keeping the sand out of it. But it's not cut right through the state park beach where all the surfers will collect. This is right at the edge of the property. So things turned out for everyone except for the developers who wanted to make the most expensive real estate in the world at the time. So with that, I'll stop here and go to my clips. Let's see. Here's the oblique breakwater idea. And the really nice thing about this is you can now increase the wave height. You can more than double it because the waves are nonlinear. We're assuming, of course, 100% reflection along this boundary here. But look at the number of peaks that you get going down the beach. So the hot dogs that run off all the groms from this spot, the groms can go down here and learn how to surf. But I'm hoping someday some entrepreneur with a lot of money would be willing to build a oblique detached breakwater like this to create some surf break. So let me stop that one. Okay, here's the, can you see this? Here's the,
We can see it.
sharing my screen.
Yep, you can see it.
Yep, okay. So here's that feasibility study for a surfing reef in Brevard County. And you can see, you get two nice takeoff points with very oblique peel angles. So you'd have lots of time to do acrobatics or whatever. But again, it only has two takeoff points. So here are typical waves coming into the project at Long Beach Island, Surf City. And it's a little hard to detect, but there is enhanced reflection coming off this this steeper beach face. You can certainly see how compressed the surf zone is, and that it took, like I say, it took nearly 2 years for the fill to equilibrate and for surfing conditions to return to normal. So I think if we got a little adventurous with the way we build beach nourishment projects, like I said, instead of being villains, we'll be heroes to the surfers, at least for a little while. And then I think I got one or two more. Well, as you can see, there are a bunch of surfers in the water. This is right next to the Jack's Pier here in Jack's Beach. And right away, we get really good data on the peel angle. And we can, by doing some clever Python work, probably we'll be able to get speed of the surfers and you know, the paths of the break points and all those sorts of things. So I'm really excited about the potential for drone technology to finally give us some data on that all important sign of the peel angle. And then, yeah, that was my favorite ride right there, that last one. So you can see where the waves initially start breaking would be the horn of each one of those surfing shoals. And, you know, it really just depends how long they last, depends on how big each one is. And of course, there are other considerations that we'd have to look into, like these would almost certainly cause rip currents in between each of the shoals. So we'd have to be a little, do some investigation of that. So anyway, I think that pretty much wraps it up for me. And I'd love to entertain any questions or hear any discussion from the audience. And
the first one was, could you share the slides or references to the articles and technical notes that were in the slides? This was from Edgewater. And we can, I can work with Dr. Daly to see what we can do and have some notes. Ultimately, the video will get posted to the COPRI website, and we'll have some notes in there so we can do that. And then I think at the last slide in your presentation also had the references too, right? Is that correct, Dr. Daly?
yeah, I tacked on beyond the end a couple that one extra slide that had my egocentric references on it.
We can put those in the presentation notes then, so that should.
Right. Yeah.
All right. The next question was from Chase, who said, do you think that the oblique detached breakwater would cost significantly more or less than the artificial reef that you referenced earlier? Thank you.
It would probably be on the same order of magnitude in cost. It should be a little easier to build because you can use, you know, you don't have to position things underwater, but you certainly get a lot more bang for your buck. You get a lot more surfable break and a lot more happy surfers than a handful fighting over on 2 takeoff points. So, and the fact that that the oblique detached breakwater idea will actually make surfable waves out of waves which are otherwise too small to surf, which is what happens at Sebastian Inlet all the time.
That Uriah asks, have you investigated whether there would be any longevity differences for a nourishment using your proposed surfing shoals versus a linear fill of equal volume? And part two, have you proposed this in any locations and received public or shareholder feedback? So does putting the horns in change the nourishment project longevity or from a nourishment?
Right. That's a really good question. And if it did, it would certainly help the cause. I haven't looked at that specifically, but I did ask, I'm sort of a fan of rainbowing rather than pumping sand up on the beach and pushing it around with a bunch of bulldozers. And I asked a well-known dredging contractor how much they would save if they could just rainbow and wouldn't have to run bulldozers around on the beach and rake afterwards for sea turtle nesting and things like that. And he sharpened his pencil and he speculated they would save about 1/3 of the cost of the project. So you could pump a lot more sand and have a much longer lived nourishment project if you didn't have to run bulldozers and move it all around. Of course, there's concerns about turbidity and things like that. I've asked the Corps of Engineers, why don't you rainbow? And they said it's usually an issue of turbidity when you're pumping sand directly into the surf zone. So that would also have to be something to be investigated.
Part two was, have you proposed it in any locations and received any public or shareholder feedback?
I've proposed it at several FSBPA conferences and things like that, but no one came running up to me afterwards and said, what a great idea. I got a project. It's really hard to get people to change the ways they're used to doing beach nourishment. So the answer is no. There hasn't been any activity in that regard.
All right. I think that relates to this next question from George, who said, has there been any constructed or monitored examples of beach sculpting nourishment projects to improve surfing? So
the only one I know of is the one that I showed there at Mayport, and that was a much bigger salient than or surfing shoal than I had in mind. But the anecdotal evidence is that it lasted more than 2 years. I had when I was at Florida Tech working on this, someone from Jacksonville called me, and surfer called me and said, man, this is great. They should do this all the time. It was one of their favorite surf spots. So if we can, again, kind of get away from the idea of making nice straight beaches and pushing things around with bulldozers, we might make this happen and save some money.
Okay. And that's kind of segues into the next one from Dylan, which was, are you aware of any locations where bathymetry was intentionally altered, for example, dredge pits or sand disposal sites, to change offshore refraction patterns to improve wave surfability? So
yes, in Australia, I forget the name of the location. In Australia, they did do essentially a berm or a submerged sand pile, and we're quite successful in creating really nice surfing waves at a location where the waves typically just closed out right on the beach. They would break right on the beach face. So they built an artificial sandbar offshore, and I'm sure if you poked around on the internet, you'd probably find some YouTube video of it. I think this happened about 10 years ago.
for that. And I realize we are right up against 1 o'clock. We have about 4 more questions that I see, so we'll keep working through them. If you have time to stay on, please do.
Sure.
Briston asks, regarding utilizing the drone to collect data, have you considered including a temporary wave buoy or an array of buoys combined with a recent bathymetry survey and beachside camera to relate swell characteristics and bathymetry to breaking wave height and speed?
Yes, if this summer we hope to, I'm actually going to teach a special topics class, trying to apply drones to coastal surf zone issues. So we have plans to put a ADCP, directional wave gauge, right off of Jack's Beach there, in self-record mode, bottom mounted, and as I say, yeah, we'll probably have to take simultaneous video from the beach looking out to estimate the wave height. Haven't quite figured out how to pick out the height of a particular wave as the surfer zooms along it. So that should be an interesting ocean engineering problem. But I'm really excited about the hovering overhead drone. In fact, I just got word the school is going to, UNF is going to buy a pretty heavy lift drone with LiDAR. We might be able to use LiDAR if it reflects off the water surface, but that'll be a learning curve for me.
All right. From Michael. Hi, Dr. Daly. When you look at the peel rate and the angle from the incident wave effect on the wave peeling surfability, did you consider the effect of bottom contours, or do you assume regularly spaced contours? I did lose connection for a minute, so I may have missed the answer.
The application of the shoaling, yeah, in a word, we neglect refraction, and so we're inherently assuming, yes, that the waves are coming, at least from our formula, the waves are coming directly on shore. But back in the day, I did try some work with waves at oblique angles to the bottom contours. But I didn't get real far with it. And most of the waves, except that some of the famous point breaks throughout the world, you're usually dealing with very long, straight, almost parallel contours. So the breaking is usually due to intersecting wave trains that give you longshore variability in the wave height. If we did go back and look at that one tape from the drone, you could see that there are actually 2 wave trains coming in from different directions there. The other thing I've noticed is the KP waves, hexagonal waves that you get for very nice long period swell. They have a section that is very oblique to the shoreline. They make a hexagonal pattern rather than a diamond shaped pattern when they come into shallow water. So there's a lot to be explored.
Next one, find the right one, from Claudio. Nice talk, Bill. The reflection wall at Sebastian Inlet reminds me of Fowler and Dalrymple's experiments. They were conducted in a rigid bottom. I have reproduced the bidirectional experiments on a model with sand and large cuspates, and sandbars were formed. How does the bottom look at Sebastian?
The bottom at Sebastian The north fillet is, as you can imagine, very dynamic. It accretes a lot during the winter and erodes a lot during the summer. But the old school surfers who were there when they first extended the North Jetty said that First Peak actually worked better before the fillet grew out. So I don't think all the years of surveying there, I don't think they ever surveyed with lines close enough to resolve any features like you're speaking about. But that would definitely be something wonderful to do on one of the few days where the weather there is clear enough to use blue-green LiDAR and really map the details of the bottom. But so in the summertime, First Peak actually works better than in the wintertime.
Jared asks, how big of a difference do you think an armor stone detached breakwater versus a sheet pile breakwater would make in terms of the reflected wave being clean and sizable enough to enhance the surf?
That's a good point. The conceptual designs I've done are actually concrete sheet pile construction with batter piles to hold it up. And so it would get 100% reflection. There are concerns about, is this going to, disrupt the longshore transport too much, et cetera. And people have talked about, well, let's put in piles, but just put reflective panels up around the mean water level. And that would allow sand to go underneath the structure and by the structure. And any bed forms would be, as the earlier question was, would be due to the behavior of the reflected and incident waves. You might get some interesting bathymetry next to the structure. But I would, if I were to build one of these, I would build it out of concrete sheet pile. And I have a whole nother presentation trying to sell this to FSB people at FSBPA, because it would be, you're creating, on one side, you're creating a quiet zone where, children and the less hardy swimmers can swim. You can fish off it, although the Sebastian Inlet experiences, the fishermen and the surfers don't get along very well. So you'd have to have probably an armed guard there on the structure if you included fishing in it, but you could do snorkeling and lot of recreational opportunity besides surfing.
All right, we have two more questions. This is from Jay Cox, who said, Bill, is there a minimum reflectivity you desire for the detached breakwater? And is there a preferred angle with the shoreline for optimal reflections?
Yeah, the second part, we did a group of students here as their senior design project actually built a small outdoor wave basin and played around with angles of reflective structure. And they maintained they got the best behavior of the waves for surfing with an angle of around 30 to 33 degrees. If you noticed in the slide, Sebastian Inlet's about, I think it makes 27 degrees, something like that. An angle to the shoreline. And then, Chris, can you tell me the first part of that question again?
The first part related to, is there a minimum reflectivity value?
Oh, right. Yeah, I would, well, for instance, Sebastian Inlet is not reflective enough because it's a crib structure and it only has rubble up to about the mean water level. The reflection you get is really not as good as it could be. And 100% reflection is probably going to give you the biggest waves and more surfing time as the year goes, you go through, especially the summer months. But again, if you tried using panels or something like that, I think this is a great opportunity for some physical modeling. It's we did. Oh, by the way, when we built the 1/35 scale model of Sebastian Inlet, we had all the 6 or 7 of the hot dog surfers that quote own First Peak come look at the model and give it their blessing. Does this really look like First Peak? And they did, including let's see, what do they call him? His name escapes me, but he was the first East Coast surfer to win the World Championship, and he used to surf there in the 70s when they first extended the jetty, and he thought the model did a pretty decent job of representing First Peak. So I think physical modeling is really going to help a lot.
And then the last question that we have right now is from Jimmy Hill, who said, great presentation. In getting public approval for surfable features, is there any data that supports these features as also providing an extent of coastal protection and resiliency for the community?
Putting such a structure out there is certainly going to cause a salient to form in the shoreline. And I see it in particular as a way to deal with structures that are encroaching on the beach. For instance, here in St. Augustine Beach, we have a hotel that clearly is encroaching on the beach, and the Corps of Engineers has a 50-year nourishment project that goes on there to fill this beach out. But when they build that project, they actually landlock the St. Augustine fishing pier. So for months after this project is renourished every 7 years, no one can fish off the pier because it's dry land underneath the pier. And this would be a much better option in my opinion to protect that encroaching hotel without having to use nourishment.
That's all the questions I see. I didn't see any hands raised and any indication that I have. So Sean, did you have anything you wanted to add before we wind down? Thanks everybody for joining. Bill, thanks for the very interesting presentation. Sean, did you have any comments from the COPRI? ASC?
I just wanted to thank everybody for registering and showing up for this webinar, and thanks to Bill and Chris for getting this out there. I know that a lot of people were really excited for this topic, and I think that it was very informative. And you can always find all of the other coastal engineering sciences webinars that we've done on our YouTube channel. And if you have any questions, just always feel free to reach out.
All right. Well, in that case, thanks everybody for joining. Have a great day.
Mahalo, everyone.
Thanks. Have a good one.